Hello everyone, my name is Fereshteh Sadeghi, and today I'm going to talk about domain invariant and semantic-aware robot policies for the context of visual navigation. So robots are good at doing physical tasks. However, human interacts with the world heavily with semantic objects. So can robots also understand semantics, and would that help them become domain invariant? So to articulate that, let's watch a video. In this video, the robot is tasked to reach a teddy bear. To be successful in doing these tasks, the robot needs to understand walkable areas, avoid collisions, and target the target object, recognize the target object. So you might argue that the world contains many other different objects and a huge number of different other environments. So instead of learning a repertoire of motion for doing different tasks, we ask the question, can we learn a single policy for doing a diverse set of semantic tasks? So by that we mean how to learn a single model that can have zero-shot generalization to unseen situations. And essentially, we are aimed to propose a method to become the domain invariant by disentangling semantics from physics. So to learn physics, we use a domain randomized simulation environment, and to learn semantics, we use static real images annotated by human. And we use their interplane to learn the policy. So in this work, we are using different scenarios, and in each scenario, the robot is tasked to reach a visually indicated goal, which usually involves taking turn around different room furniture. We propose DIViS, which is a network architecture that integrates physics and semantics. The physical aspect of the task that we are looking at involves collision avoidance. To do the collision avoidance, we use our previous work, CAD2RL. CAD2RL can find collision-free directions to navigate to different free spaces. And it has a fully convolutional neural network architecture. To learn semantics, we use an object localization network, which is pre-trained with natural images, which are static but are annotated by human. And this network also has a fully convolutional architecture. By concatenating the semantics and physics features, we train a control network that navigates the robot toward the target goal. And our control network is recurrent, which has a recurrent LSTM unit and is trained entirely in simulation. So for training our controller network, we use deep reinforcement learning by doing multi-step dense Monte Carlo rollouts. And although this controller is entirely trained in simulation, it can generalize well to real-world situations and unseen environments. So we have tested our method in various domain randomized simulation environments, and being successful in doing these tasks involves moving around different room furnitures in very confined spaces. And we have compared quantitatively with other results, and DIViS has outperformed other methods with a significant margin. We have also tested our method in real-world environments, both qualitatively and quantitatively. And all these real-world scenarios are entirely unseen at the training time. For doing the real-world test, we perform and use two different real robot platforms, which have different height and have different RGB cameras. As you can see, our method can perform well in diverse set of scenarios, such as reaching a chair in confined spaces, or an oven in kitchen, or an umbrella in outdoor, and many, many other scenarios. And roughly, we have gained about 82% in real-world scenarios. To conclude, we propose to disentangle semantics and physics to learn domain invariant policies. And we use very cheap simulation and real data. For more details, please come to my poster. Thank you.